Okay, do you hear me now?
Yes.
Yes, we can hear you.
Okay, so this is the course of plate and shell structures, or actually the mechanics of plate and shell structures. I think that I will start sharing the slide. Here, now you should see the slide. Do you see the first slide?
Yes.
Yes.
Okay. So this is one of the courses which you can choose. So I think that there should be about 20 students after the compulsory courses, about 60, 70, 80 students. And this is just a normal master level, doctoral level actually as well, if somebody wants. And 5-credit course. And the topic is practically the mechanics of elastic plate and shell structure. So we are not studying, if I remember correctly, nothing but elasticity. And then, of course, I usually go to bars and beams and membranes just to make things easier. Kind of start with those and then go to the plate and shell structures, which are a little bit more complicated. I will give the first 5 weeks, and then Antti Niemi, he's a professor in University of Oulu. He will give the last week. And then we have 2 assistants from my group, Jalal Torabi, who is a postdoc, and Tomi Kankkunen, who is a research assistant. Are you there now?
Yeah, I'm here.
Okay, maybe, I don't know if you can, let me check. Can you show your video screen just to say hello? Or
Yeah. Just a second.
so Tommy is giving one of the exercises. Now I have added 2 sessions. So we have 2 exercise sessions, one on Friday and one on Monday, so that usually when I'm giving the lectures on once again on Tuesday and Thursday, then you have time to read, especially now there's quite a lot independent studies required. And then on Friday, you can already have some ideas about the exercises and something to ask. And then on Monday, you can continue so that on Tuesday you can return. So now it's only theoretical and reading exercises, and practically no computer exercises. We might have sometimes something like, okay, plot by using any software, MATLAB, MathCAD or Mathematica or whatever, plot something, and that's it. Okay, then Jalal, are you there? Maybe Jalal is not present here. Okay. Anyway, otherwise the way of going, the practices, course practices are practically identical to the ones of the sorry, of the basic course. If you just skip the or drop the computer exercises. And what should I say? Yeah, then we have only one book. Well, actually, I give you for the first week, I give you some reading material from another book, because we are going to study 2D and 3D stuff, and it's not included in this book of plates and shells. And this is quite a classical book. I think it's not, might be even not the first edition, 2001, but a little bit older. A quite nice book for students of your level. And it should be, of course, one of the I mean, when choosing a book, it should be a book that is in the library. And sometimes it's very difficult to get some. I actually tried once one book for one course to get it in the library, which was practically impossible. I mean, it was kind of too expensive for the library, because usually it happens so that the editor and the publishers, they force the library to buy a huge package of books, and then one book is included in one package. And if you want one book, then you have to buy the whole package. You know that it's something like this also when movie makers sell movies to the broadcasting companies. Okay, but this is the way. But this is the one that I wanted, and it's there in the library. And now I think we can go to the, let's see if we can get there. Now, do you see the course page?
Yes.
Okay, so this is the course page. I have collected all the information here. So you should include your name in the web audit system. Here I have practically the same information. And now it's even more, about 60% is independent studies if you calculate the nominal hours. So in practice, I would say that, like in the previous course, when I'm having a lecture, then you usually should read a couple of hours the material, or the material what I give in the first exercise. So practically 2 hours reading after a 2-hour lecture. And then you start to make the first exercise, which is the mind map usually, or some essay type stuff. And then independence, sorry, yes, here. For exercises, I mean, if exercises are now 2 times a week, then it's even more for those, practically 2 times that you should do alone. Of course, in some cases, and in here in this fraction, I think we have to lower this a little bit. I don't know if you are aware of the fact that if you are studying 2 or 3 courses per period, these nominal hours, what we are given, mean 58 hours per week in total. So it means that you practically, if you study a little bit less during the examination week, then it means that it's 60 hours per week. So it's quite a heavy week, 6 weeks, 60 hours per week. These are the nominal if you take 3 courses, and this is the case when you study the compulsory courses during one autumn, which is quite stupid, at least to me, because it's far too much. And the only way is to reduce the workload of the courses, so that we practically say that you study 40 hours per week like normal people. And then it means that every course is practically 2/3 of the nominal what it should be. And sometimes if we are not reducing that, then the course feels quite heavy to you. Okay, but anyway, now I presume that some of you study only 2 courses per period. If you study 3, then you better know that it's a lot. And of course, the official amount of credits you get if you study every second period 2 courses, every second 3. But I think that in the past, at least, we used to study during the summer and Christmas period, so that some of the examinations you are taking there, this is the way to lower your workload during the periods. So this period system is a little bit heavy if you study only during the periods. Okay, here the learning outcomes. Recognize and know the basics of 3-dimensional elasticity. Of course, we start from that because all the structural models are based on 3D. And then we go to 2D and 1D. Understanding the energy and equilibrium approaches. So 2 approaches, which I will explain you a little bit later. For formulating linear bar, plate, and shell models. Ability to apply linear plate and shell models to variation structural analysis and solve corresponding partial differential equations. Of course, hand calculations without any numerical tools. We are not able to solve too many or too complex problems, but enough, I think. Ability to analyze shells of revolution in membrane state. Yeah, that's the kind of the simplest shell problem what you can have, and you can solve by hand calculations or analytical solutions in general. Understanding the edge effects in the analysis of shells of revolution. These are a little bit special issues, but still important for engineers, even for design purposes. Okay, now if we go to the materials, once again, here is a link to the book you can find, and then the last year I already gave an announcement. Maybe I should have given this announcement already during the first course, because in the feedback I got quite many actually said that I should have given the exercise slides already before the lecture, what I did in the end, but of course I kind of see it natural that the last year material, not only the exercises, but also the lecture slides can be used. And now I inform this explicitly. So usually I'm giving because maybe some discussions during the lecture, I need to add something in the lecture slides to make things clear. And it's a hassle if I upload one set and then I upload another set and so on. I think it's better that you use the last year material, which is very close to the present one, to the new one, and then we get the new one a bit later. And okay, here the content. We start with 2D elasticity membranes practically, and then 2 types of plates, which are the most important, of course, maybe kind of the core issues for engineering after beams. And then some special orthotropic stiffened or sandwich or laminate plates as one group. And then vibrations, a little bit about vibrations, because we don't have a course on vibrations. This is why I thought about including something about, we kind of drop something about vibrations in every course, as long as we don't have a special course on vibrations or dynamics. And then shells. And as you can see, it's more about plates. It's easier and it's more relevant for civil engineering. Shells, it's more difficult, and then the rest is left to your future studies. And then I mentioned here the stability is another course. Finite elements is another course. We are practically solving all these problems in the finite element course. and then material modeling is another course, and then non-linearities, I mean material ones, will be there. Okay, and then exercise tehtävät means exercise assignments and then returns. Then you return your stuff, and that's it. So the rest should be clear. Well, maybe you can go through those on your own. And then once again, of course, you don't have to listen to the lectures. You don't have to come to the exercise sessions. You can study on your own if you will. And then it's a combination of examination now a little bit more because we don't have computer exercises, and then assignments. And passing grade, kind of preliminary guess is that 50%, but it's always depends on how difficult finally the exercises and exams will be. And then there is another exam in April, another one, of course, after the course. This is maybe should be updated. Okay, and here once again the content. Now, do you have anything about practicalities? Anything to ask? Any questions?
Could it be so, like it was in the engineering computation and simulation, the previous course, that it would be like a 50-50 homework and exam?
Why you mean that? Could it be like that?
Yeah, could it be?
Well, of course it could be. What do you think? How about others? Is it too much if the examination is getting? I mean, if the exercises are only 30.
Well, it's a good idea to increase exercise weight, so we have more chances to pass the course at least. But of course, the target is not to pass the course. The target is to get a good comprehension of the course. But yeah, maybe we increase the weight of the homework would be good.
Okay. Of course, maybe once I've tried something like this. I don't know. Actually, I don't remember anymore. But so what should be? Should it be 50 or what should be? What do you suggest? 50 or 40 or now it's about 30, or was it 1/3?
Maybe 40-60.
Sorry.
40-60, yeah.
Okay.
Of course, other students can vote as well.
Yeah, because I think maybe if I give 50, then especially if finally, okay, then maybe I don't have to lower the limit for passing the course. Then it might be possible to keep it there, but of course then it's a little bit. I mean, in principle, it's possible that you are not doing your exercises on your own, but your father is doing that stuff or someone else, and then you pass the course. I mean, if you get all the exercises done and then you get one. Officially, in our program, we have discussed a little bit this thing that actually some professors don't like the way I'm doing in the basic course, that you get a lot of exercise points, almost, or was it? Yeah, it was 50%. Even more if you think about project work, so that the examination should have more weight. Maybe then I would raise that to 40 or something like that. I can think about it. If there are no objections, somebody who wants to keep the weight on the exam.
I mean, I think it depends on how difficult the exam ends up being and how difficult the homework is. Because for the basic course, the computation and simulation and engineering, there was, I think, some of the questions were such that we hadn't really covered much of them in the lecture notes. So one really had to understand the mathematics of differential equations, for example, to solve the problem completely. But if the problems in this course in the exam are more similar to the homework, at least like on a conceptual level, then I don't know, then it seems reasonable maybe to put more emphasis on the exam.
Okay, yeah, that's also, of course, I kind of added a little bit more kind of application skills needed in the exam now, because it was an online remote exam. Of course, not much, but it's very often if you are studying these things for the first time, then of course it looks a little bit kind of too difficult. Even let's say that when you see the model solutions, what I'm giving you soon, then you understand that it was not that difficult. But when you are in a hurry in an exam situation for the first time and so on, then it's applying is always a little bit difficult. But okay, I can think about that 40, 30, 50 issue.
Actually, I have one quick question regarding the homework. So is it okay to just use pen and paper and then scan a clear picture of the answers?
Yeah. No, nothing else is required. Of course, I think that some of you, even in the exam, you used maybe Word or some other writing software. But I actually recommend using pen and paper, especially in exercises. Of course, sometimes it might be difficult to read, but usually I think it helps in learning. When you have to do, I think that there are even very rigorous studies on the fact that by using your hand kind of body increase the brain activity as well. Okay, but it's anything goes. So it don't have to be so formal, nice reports. Okay, let's go to the topic then. If or is there still somebody wants to ask? I think that some of the exercises will be identical, especially now it's a very standard classical topic. Some of the exercises you just have to go through some calculations what people have done for let's say at least 50 or 100 years, some small examples. So you don't have to apply, you just go through things. Of course, in some exercises I add a little bit kind of differences or some twist, so that you are not able to just copy the model solutions or some others what you can find in the internet or in books, textbooks. Maybe I think I had somewhere. Maybe it's coming. Okay, let's see. Anyway, yeah, this is first we are going through the strong and weak forms for 3D linear elasticity. We are a little bit recalling and then actually I should have added here 2D as well. And then, well, okay, it's coming plane strain and plane stress problems. So these are the fundamental problems that kind of are behind the membrane and plate and shell formulations. And then, of course, you should recognize the differences between the dimensions and understand the basic features and ability to solve some model problem. problems. By the way, have you been able to download the book? Anybody tried?
Yes.
Okay, so
works.
is it so that you need to you can download the whole book or just some fractions of that?
Well, you can download either, but the maximum period is 7 days, and after that files are not working, you need to download it again as you are
Really?
borrowing it again.
Actually,
That's the online ebook.
Or
type that book name to Google. Don't use any Aalto, Finna, or anything like that.
Well,
There's
that's
a
another
free
option.
PDF.
yeah, you can find a cracked PDF definitely. But I think that when it came to us, actually I downloaded the whole book and it's still working. I don't know, maybe they have changed the license. By the way, yeah, remember always to use the VPN connection or some other connection so that you can get access to those library materials. And then, of course, I just list here that we are going through or kind of relying on the basic course material, and then some courses of bachelor's you have studied continuum mechanics. I don't know how much, depends on your background, but at least in Aalto we have one course, and then we have course of, maybe I should have written here also the course of solid mechanics. So I think we have two courses. Of course, statics and dynamics is always kind of the high school extension, but it's not about the continuum. Solid bodies, it's kind of rigid bodies. And now there are two ways. I have now used number 2 here, and I'm using that in the slides, especially because the book is using number 1. So what I mean here, maybe I can, I don't know, where is the, damn, where is my drawing system here? What I mean that usually, I mean, like we did, I think in some exercises, we draw this kind of dx short piece of material, and you can do it, of course, in 3D. And then you write balance equations and all these things, and then you say that, okay, let's see if, what will be the differential equation. And the other way is that we start from the integral form, and then we plug in all the or insert all the kinematical assumptions and things like that, and then see what happens. So this is the way I'm using here in the slides, and of course both are possible, but usually in more complex problems the first one is not a viable option. It's too complicated, and you easily make mistakes. Okay, so these are the two ways of working, and I think that, and then of course I try to build a link between these two during the lectures a little bit, so kind of give you a direction. But when I'm giving you the reading exercises, you will get to the option 1, number 1. And now if we go to the previous studies, especially the basic course, what I'm recalling, of course, you remember here that we were modeling something, and then of course it's always the physical problem is always the starting point, but it's very often too complicated, so we have to make some reductions, and of course the first reduction is that if let's say that you are now we might say that now you are here. Let's say that you have multiphysics. Of course, in structural engineering, it's not very multiphysical stuff, but in general, you have multiphysics here in the problem setting. But then you go to, let's say, monophysical, which is our case. Of course, it's only mechanics, but it can be still 4D. And then we go to 3D, and then we might go to 2D and finally 1D in some cases. But now plates and shells, it will be this 2D. So all these equations and many other things, they will be considered in the 2D form, which is quite nice because it's quite simple in some cases. But then the problem is that actually it's more difficult than 3D in some cases, like in shells. You have to add a lot, kind of a lot of descriptions or tools or so there are the components are quite sometimes quite complicated. But the 2D some 2D problems are very simple. It's like 1D bar. It's simple. Then I think that 1D plane strain problem, for instance, is simple. Or plane stress. Okay, and then what we are usually studying here, it's first of all linear. Maybe I give you an idea about geometric nonlinearity. It will be touched only slightly. And then isotropic, but in our case, we also have anisotropic, if you remember the sandwich and other composites. So we are studying also anisotropic stuff. And time independent, yes, but then somehow when we are studying vibrations, of course, first we assume that time is involved, and then we show that actually if we have a free vibration case, time kind of disappears and we get a eigenvalue problem. And so this is almost time independent stuff what we are going through. In the basic course of in the second course of finite elements, I'm going through some time dependent problems, and then I already went through something in the basic course. Okay, so this is the concept, and now it's all about idealization or modeling error, nothing about discretization. Maybe in the end, I'm showing you a little bit about some practical tools, especially for plates, where we use numerical, it's kind of semi-numerical methods, but not true finite elements or something like that. Okay, so let's move on. Here, of course, we are going to 2D, and because we want to model plates and shells and membranes more easily than just as 3D bodies. But of course, one reason in the past especially was that we would like to do hand calculations, because that was the only way. 3D problems, no way to solve before computers. But for the whole history of mechanics is full of different hand calculation techniques and different models suitable for those techniques for 2D and 1D problems. I think that even the concepts of plates and shells and membranes are kind of coming from this direction. Otherwise, you cannot solve anything. Okay, then I'm recalling very quickly these just before I draw one picture, or maybe after the break, kind of explaining these, which is a nice framework. But I remind you about it's about deformation, of course, or motion when we have time in continuum mechanics, and we usually speak about these four issues, which are kinematics. So it's about displacements and strains, and especially the relation between them. And of course, in 1D, it's the easiest to remember. I think it's 1D is a really nice bar problem. Is always a nice example because we kind of remember that what we're doing. And then kinetics, it's a little bit, I mean, difficult to remember that both are kind of kine starting, but it means conservation of linear and angular momentum, and the conservation of linear momentum gave us the balance equation here. If displacement and strains were there, then the linear momentum giving us the balance equation. And actually the angular momentum, is there anybody, do you remember what was the angular momentum giving us? Balance or conservation? Okay, we will see this after a while. And then the first and second law of thermodynamics, and that's a little bit difficult because when we are not studying really kind of thermodynamics in the sense that we are studying dynamics or thermal, it seems that they don't affect at all to these problems of mechanics, I mean solid mechanics, but actually they do have some effects. For instance, okay, maybe I will give you some information later, but here they affect a little bit, and then here in the constitutive equations a little bit. And then the form of constitutive equations is stresses versus strains. It's this now here generalized Hooke's law or something like this. And then, of course, vectors and tensors or matrices are needed. Differential, integral, and variational calculus is needed. A little bit partial differential equations are the strong form results. Okay, so that's enough. And then what we have to remember that of course, now when we are dealing with continuum mechanics, we are usually in the macro or meso level. And in civil engineering, especially if you're not going to materials, let's say concrete or materials or wood as a cellular material, like you can see something here, then it's not about micro or nano. And so this is the kind of the world that we neglect small details in the material level. Other small details we might take into account. Okay, this is just about that fact, and then here it's about the same, that we are overlooking or how to say it, I don't know. So we are kind of thinking about homogeneous materials and large scales, and then we must continuously differentiable. So we must be able to use some tools, mathematical tools, otherwise we don't get anything. and then all materials in the sense that we can say linear elastic materials, plastic materials, so we kind of group different materials together. We don't say that this is for wood, continuum mechanics for concrete or steel, but they are all, it's from the phenomenological point of view, you classify them. What I'm studying actually today in my research is so-called generalized continuum theories and numerical methods for those. And there the idea is that you try to take, in some cases, you should be able to take into account the microstructure, what you have in the material in a better way than just assuming that it's finally homogeneous. Okay, let's go further. And then, of course, when we are studying continuum mechanics, you should remember that we are thinking about solids, but liquids and gases are practically following the same laws and all the same principles. Almost practically nothing is different. They just appear in a different form. Okay, maybe something is a little bit different. But we are here, of course, focusing on these. Now, for simplicity, elasticity during this course, and plates and shells, but also bars and beams as a background. And then the numerics comes to the question during the next course. And then if you remember, we already did something like this. We started from 3D, and then we derived a 1D model for bars. This is just one of your exercises, and now we will do something very similar for membranes, and then we get these equations, differential equations or weak forms. And that was one of your exercises. So start from the 3D and then insert a kinematical assumption, which of course is not just a kinematical assumption, but it has some reasoning behind. For instance, of course, one reasoning is that this is a long, looks like one dimension is longer than the others. And then it looks like the force is acting only in one direction. So these are the main, then you can say that, okay, aha, the displacement in x directions is practically the only thing what I'm interested in about. And then the corresponding strains and stresses and so on. But now before going further, then I will, according to this, I will draw a general picture where you kind of see that why and what we are doing. And then we go to the membrane, 2D, 3D membrane problems. Maybe here I'm going to draw, but let's have a break first. So let's have a break of 15 minutes, or do you have any questions now? There's one question in chat. Okay, it was just about this issue. So let's have a break and then we start on after 15 minutes. Okay, do you hear me now again?
Yes.
Okay, thanks. So let's continue. Okay, so before going to the 3D descriptions and then to 2D descriptions, let's start with the basics in the sense that maybe I should have drawn this kind of picture already during the first course, because this might help you. I was thinking about, especially now when you have a force, which is usually the case. Of course, you usually have a structure, and it's a 3D by definition. And then you have a body force. Of course, you can have other forces as well, but let's think about those later. But body force, for instance, gravity, you always have. So this is a good starting point. Then you might have some service loads. We call them service loads in civil engineering, but well, internal and external loads of different kinds. And of course, when you have a loading, maybe it's a vector here. What do you want? You usually, from the practical point of view, at least, you would like to get displacement, I guess, because you know where it's moving, where the body is moving. Especially when it's about if you have time here included, then of course you want to know here x is x, y, and z, and then time involved. Of course, you want to know the motion. And then how can you get it? I think what is the, let's say, what's the most most intuitive way of getting from a force displacement? If you take real life or whatever situation, how do you get it?
You somehow integrate, or you find out the force and the stiffness, and then you divide the force with stiffness in the
Yeah, but if
but
yeah, okay, but if you don't think about anything like stiffness or any theoretical issues in practice, how do you get if you have a stick and you bend it by a force, how do you get the displacement? I think you do a measurement. I mean, you can experimentally. So let's say that you have experiment. Oops, interesting. So you have force, and then you want to get displacement, and then of course you can get it. One way is to make an experiment. But this is something that you should repeat quite many times. Let's say that you have different sticks, you have different structures. You should actually always do one experiment, another experiment, depending on the situation. And this is the problem that you have to solve. And this is why we have the theoretical considerations like solid mechanics or continuum mechanics. And how we do that is that you already know that from, if we can actually call this force x, oops, external, and then we have internal, and of course the internal counterpart is stress. We can have a vector or usually a tensor matrix. And then in between those, of course, we have, what do we have in between the force and the stress?
The area.
Sorry?
Is it the area?
Yeah, well, yes, area in the sense that if the force is acting on, or stress is defined by force per area. But now I'm thinking about more globally. That's a kind of the one point. In one point, the stress here actually, it's good that you notice this one. It's stress at a point x. Okay, maybe I even add here time, if I have also time here in the loading and here in the displacement. But what is the sorry?
So I guess it will be the location or the distance for that point.
Okay. You mean maybe you think about moment.
Yeah.
But let's say that, okay, maybe we I leave it open. Let's go to the other side. Now we're thinking about the other side. So what do we actually get? What is the usual? What is what we have? It's kind of internal issue, but what do we get from displacements?
Strains.
Yeah, strains. So we have here strains, and then we already have actually this that we write a strain. It's a lot of definitions already, and then I used to write here. I think I wrote it like this, but this is the symmetric gradient of the and of course it's simply in 1D. It's u prime epsilon x is u prime x is the derivative, and this equation was called the kinematical. So this is kind of the kinematics kinematical part. Here on the right hand side. And then what do we have between stress and strain on the bottom? What do we have there? What is stress in terms of strain, for instance?
Is it the youngest modulus?
Yeah, let's.
Yeah, sort of.
So if you have 1D, now I write always the 1D case. Let's say that this is the 1D example row, and then I can still write sigma at point x and E times epsilon x. But in general, we actually have here, it's a little bit complicated, but we should write a fourth order tensor and the product of that with the strain tensor. But usually, maybe if we write sigma as a vector, what I will do next. So if we still write sigma as a vector, then we can write E as a matrix and strain as a vector. And if you remember, that was called the Voigt notation. I will explain or remind you about that a bit later. But now you can even think about the 1D stuff. You don't even have to think about the tensors yet or any vectors. And that was called, what was the relationship between these called? If this one here was the kinematics here on the right, what is this equation? Of course, this is displacement. Oops. Displacement strain relation, and this is stress strain relation, and it was called constitutive. Relation. So the material, how material behaves, and of course it can be something else. If it's plasticity, then it might be very complex and so on. If it's viscoplastic, it's always here. It's always a relationship between stresses and strains. And now we are still missing the relationship between stresses here and forces.
That's the kinetic equation, isn't it?
Yeah, it's kinetic. So if I write it here, kinetics, and then it practically means the balance equation. So it was usually, I wrote it with minus divergence of sigma equals F in 3D, but of course it's simply minus sigma prime equals F, and usually then in this case it was Fx. But of course it don't have to be F. Oops, shit, now it's gone. Undo. Now it's there, back there. And then we are almost ready, I think. Of course, it's a little bit messy. You can draw a better one on your own. But the idea here is that when we are given a force, sometimes, of course, you might be given a displacement and you actually have to find the force. But usually it's a standard way of thinking that you are given a force and then you get a displacement. You try to find a displacement, and of course, or you can even say that you're not interested in the displacement. You are given a force, but you are only interested in the stresses. But then anyway, if you are going from, let's say that you are going from forces to displacements, you have to go this route. So you have to go here. First the balance equation, then you have to go here. You have to build a link between stresses and strains, and then you even have to build a link then between, because you kind of from forces to stresses, you actually introduce a new notation, new quantity, stress. Then stresses to strains, you introduce a new quantity, strain. And then you have to build a link between strains and displacements. And this is a long route, but this is what you have to do if you're not able to do experiment for every single structural part of your building. You should do an experiment, and then for every joint, you should do an experiment, and finally, maybe for the whole building, maybe for a small scale experiment all first, and so on and so on. But because this is something that we don't want to do in engineering, then always. Maybe we use the experiments for calibration, but otherwise we should do a series of experiments for every single different case, because you can never, if you are not aware of this bottom, let's say that this is a surface of a sea, and if you are not aware of this thing that is happening below the sea level, then you only see the forces and displacements, and then you only do experiments. And this, of course, has been the kind of old way of doing engineering in the history. And we still do it for some purposes, like calibration or validation of these models. And then what we have used here, if I go a little bit back, you see that I listed somehow here, where here, kinematics and kinetics, thermodynamics 1 and 2, and constitutive. And now it seems that thermodynamics 1 and 2 are the ones that are not kind of visible. Kinematics it was the displacement strain. Kinetics it was the balance. Actually, one of them was not. It was only the linear momentum balance. And then constitutive was there. But now if we go back, and I should actually write here inside, I should write the thermodynamics 1 and 2. Somehow they affect here. And then in the kinetics, I should actually write here that sigma transpose is sigma. So it says that sigma tensor is symmetric, and that comes from the angular balance of angular momentum. We usually don't write it because it's kind of assumed that this is the case. But officially it should be written with the field equation, with the balance equation. And thermodynamics 1, for instance, here, it gives you something about, okay, depends on the way how you number, but usually 1 is about this stuff here. So it gives you actually also the symmetry of the strain tensor, or something about the strain displacement relationship. And then thermodynamics 2 gives you something about the constitutive matrix. Like in engineering, we usually say, where is my, here is the Young's modulus here, and we usually say that Young's modulus is positive. It's quite natural. And then what else do we say? We actually say that Poisson ratio is greater than and smaller than, and then now the question is what? do you remember what are the limits for the Poisson ratio?
Smaller than 1/2 at least.
Mm. And 1/2 was for, or almost 1/2 was for
Rubber, I think.
rubber-like, yeah, so incompressible materials. And then, if I remember correctly, it's -1 here. Theoretical. Then, of course, in practice, it's very often positive. But anyway, and these come from the theoretical considerations, and you can show that you have negative Poisson ratio materials or kind of metamaterials, but they really come from the thermodynamics second. And now we can say that we have kinematics, let's say, then we have kinetics, if I'm boxing these kind of fundamentals, then we have thermodynamics 1 and 2, and then we had constitutive, and then the balance kinetics, it was practically, you can here also say 1 and 2, because it was the balance of linear and angular momentum. And they gave, this one gave that one, and this one gave that.
So was the angular momentum, that gave the symmetry in some cases?
Yeah.
Okay.
Yeah, that gives the symmetry. Yeah, you can have continuum mechanics with non-symmetric stress tensors, but that's another story. In our cases, it's always symmetric. Okay, but now this is the full 3D, and 1D was here an example. And of course, this is something that you always have to remember as a kind of a grounding equations. And now we should go on, and maybe I will. Okay, maybe I clear this. No, it's gone. And then then of course we should remember what, maybe before going to, because if we wanted to go from the force to the stress, maybe I simply recall, this is something that I didn't do, maybe I should have done this as well in the basic course, because it seems that many of you have forgotten these. Like this. So we have a point somewhere. Okay, maybe we can have a 3D body, and then we have a point somewhere inside the body, and then you're interested in the stress if this point is x, y, z, or in 2D body. Of course, it's easier. It's x, y, and then you are interested in the stress at that point, and the stress tensor for all the stress components. And what are those stress components? Just one example, just to remind you about this. So x, y, z. And then the point is somewhere here inside. So we usually, one way is to describe this issue is that we take a box or kind of parallelogram of dx, dy, and dz. So these are this is the cube, and then we are interested in principle stresses in this point, but of course we need a small box, and then we say that dx goes to 0 and y and z as well. And then we get stresses at a point. But first we have to make a finite finite or infinitesimal box like this, and then we are thinking about one facet or face of that. And then, of course, you can measure stresses. You can have, as you remember, you have normal stresses. Now we have normal here in all the directions. And then, it is called sigma xx in this case. Why? Do you remember why do we call this xx? Why the index is xx in this case?
Because it acts on the surface that has a normal in the x-axis direction, and then the force also acts in that same direction. So it does the normal of the face and then the direction of the force on that face.
Yeah. It's usually the first x was the normal, and then the second was the direction. And the first one, you can also say that I'm thinking about a facet or face where the x component is constant. This is why one way of seeing. But more general is that you say that I have a normal, because of course we can have a face like and this, and then we just have normal like this, and x is still here, and then we can define in this direction. If this is the normal, we can say that this is n. This normal vector is n. So it's more general. but in this case, it might be said that x coordinate is constant on this face. Okay, and then of course we have other directions. It's this direction force and this direction force, and then they all have the same first x, because they are on the same surface. And then actually this is not correct. I should write it here this direction. So the other this one is xy, and this one is xz. So that was the way to define the stresses in 3D. And of course, if we are doing that in 2D, then it's another way. But I mean, it's just a simplification, or you can define it in a little bit different. But it's better always to think about a 3D body. Maybe 3D and 1D. Let's say that in 1D you usually, of course, you kind of define a normal, and then you say that sigma equals f over a, and then you put here a limit, so that limit a goes to 0, and then you have a point stress at a point. But here it's better to think about, then we get the whole tensor. And now if I'm writing the tensor, of course it was, I think I have written, so we just collect all of these here. Of course the diagonal is the easy one, and then we have to collect, if it depends on the style, but I think we write it like this, is it, or other way around? Anyway, and this is symmetric. So 6 components, and that's why we usually wrote it as a vector of 6 components. I think was it? No, I don't even remember what's the usual direction. Maybe this way. But there are many ways of writing. But anyway, 6 components in a vector. and then this is the stress, what we need in 3D, and then of course in 2D we remove the z ones, so this is what we get. Then of course the question is that what are the cases, which kind of practical cases? It's easy to show here in the matrix that this is 2D, But what are the practical cases? Then we go to those a little bit later. But I will now go quite quickly through the theory and then of 3D, because this is just recalling what we've already seen. But surface traction was the stuff that we give on the boundary of the body. So if internal force was here inside the body, and then the traction was here, so this is T. And usually, of course, if we once again, if I go to 1D, if we think about the NL was here, the traction, and body force B was here, the body force. And it was, of course, axial body force in this case. But here it has it's a vector having 3 components. So somebody's pulling you from 3 different directions. Okay, so this is the traction stuff. Then these are the theoretical things that we need to define. And actually, this one, the Cauchy's law, is practically related to the drawing that I just gave you when we were defining actually here some facet stuff, and then it has a relation to the stress with the normal. Okay. No. Then the static equilibrium. Now I'm using the energy approach. I'm not using the. Of course, I could use the drawing. Now I'm referring to the original types 2 and 1, 1 and 2, and I'm here. I'm here now using the integral way, and of course in practice this is here F, and this is ma. So it's nothing but Newton's law in a little bit more general way, because here we have rho is mass density, and then we have acceleration, which is the velocity there. And then yes.
Sorry to interrupt. Your charge is 1%.
Yeah, I know. I should maybe move a little bit. Okay, I move here. Okay, now, so let's move on. And the body forces, like I showed you here, we have tractions. We have, now I'm calling this body force here, and traction outside. And the ST was the part of the boundary where we have this traction. So it's this part. And the whole body is, of course, the whole body here is omega. And then acceleration is, of course, inside the whole body. And then what we have is here, if we don't have, I mean, if V dot is 0, of course, V dot is 0 if there is no T. So it's not time dependent. And then we have a much more simpler problem. And then what we did, we used first, we don't want to keep traction here, but we want to use only stresses. So we replaced T by sigma n on the boundary. And then we don't want to have surface integrals, and that's why we can use only by the Gauss divergence theorem, we can only use body integrals. And that's nice, of course, because then we can write B plus divergence of sigma under the same integral, dO.
I have one quick question. Is the normal included now in the somehow in the divergence clause? I mean integral, or
yeah, it is, yeah.
Okay.
So the divergence theorem includes normal, so it's only valid if you write here normal. You cannot write that sigma something or whatever something. You have to have exactly this format. Matrix or tensor or vector times normal, and then you have some kind of derivative depending on what you have here. There are different forms, but they always have this normal format. Of course, in 1D it's a little bit strange to speak about a normal, but it's still there. Okay, and then we go up on, and then we get the equilibrium equation. So this is the stuff what was under the integral, and dynamics. Now I kind of added afterwards dynamics here. So if we have acceleration, so that was the first TD. Let's if I think I called that sorry, not TD, but the principle of linear momentum. So that was kind of the kinetics 1. And then we go to the kinetics 2, which is the principle of angular momentum, and we write it, and we go on and go on and go on, and it's giving nothing but symmetry of stress tensor. Of course, it's a little bit frustrated, but this is what it gives. Okay, and then of course we can do all of these things without now if you remember what I draw you, it was this part, and actually somehow we don't have to define sigma equals something. We don't have to define epsilon equals something yet. We have done all these things for stresses only. So, but then of course usually we want to go further because we want to get displacements as well and strains, and that's why we define, of course, displacements. It's the difference between two positions, and then strains, and now I'm using here linear deformations. If you remember, if I'm adding here something like plus 1/2 gradient u times gradient u transpose, or something like this, plus blah blah blah. This is you can see that this is nonlinear in the sense that it's the second power, practically the second power of, if you have u prime, it's the second power of u prime, and that's a nonlinear strain. And this is something that you need to have in buckling problems or large displacement problems. But when displacements are small, we can say that this is zero. It's like a Taylor series that you only include the first. In a Taylor series, of course, you have here something like u0 plus gradient u plus 1/2 gradient u squared plus blah blah, and then this is now the term that we take into account, roughly like this. And then we can also define, actually when you read the book, you will see how do we define these single components very carefully, just to understand that. And then the principle of virtual work was the kind of the balance equation. So we are writing the balance like this, not thinking about a single piece of dx and writing forces and moments and so on in many different directions, but we are using the integral, internal and external integral form energies. And this is the strain energy, this is the body loading energy, this is the external loading energy. And then I'm just remembering that epsilon was just the gradient, so I'm using the kinematics. And then here from the kinematics, once again, what we are doing here, you maybe see that we are integrating by parts. So this goes here, and then we are splitting these integrals and so on. But I leave this to you because it's already been covered, and of course I will maybe include one exercise where you have to do something for this. And then this gives us the strong form, so the balance equation. And of course the balance equation, we could have got from the balance of a differential piece of material, but now we are getting it from the integral of energy. And once again, whenever you get something like this, I think it's good to write it in 1D form, and then it was something like could be like this, or you can say that it's always good to practice this, and this one of course was the same as EA U prime prime equals B. It's always good to practice this 1D bar problem, just to kind of get the idea or put it back to the basics. And then of course in linear elasticity we can also write Hooke's law in this form, which is a little bit just a different form, not without the matrix, like this. Okay, maybe the weak form I'm skipping here. We have just studied that, and then finally I remind you about the 2D plane stress, plane strain, and this is I'm giving you as a maybe as a home exercise, but on Thursday I'm maybe continuing from this on Thursday, and I'm giving you some reading material, and on Thursday I'm also calculating some 2D examples, because those I will give you also as home exercise. Usually I now try to do it so that the Thursday lecture I give you some exercises. Many of during the basic course wanted to get some example exercises. Now I'm giving those in the at least on the second lecture of Thursday. I mean the second hour, or even almost the whole 2 hours, but usually maybe the only one half. So now on Thursday, if I'm continuing from this stuff, plane elasticity and plane stress, plane strain, and we are thinking about, let's say, some practical examples of course, membranes, plates, loadings like this, loadings like that, and then we might also have long, let's say that you have a dam or a wall like this, and then if you have a dam, then water is coming from this side, and this is a long dam going actually very, very long, and then you would like to analyze only one cut here, one cross section, because it seems to be that the loading is quite uniform in this direction, and it's just a long straight line. And these kind of simplifications, what are the cases? Of course, you might have a wall, and then you have loading coming here, and then somebody is going through this door, and then it might be a brick wall or just a concrete element wall. But the idea is that, okay, when do you use plane stress and when do you use plane strain conditions in which kind of cross sections, or I don't know if this is called a cross section, maybe it's a cross section, or just a wall like structure like this. It's a plate like wall like structure. So these kind of things we will, so we are going to a little bit more practical issues on Thursday. Do you have any questions now? No questions.
Well, actually, I have one question regarding this angular momentum. So how the partial integration, I mean, I guess I could Google it, but do you maybe have some textbook material, or is there some material in older courses where it is shown in more detail?
Okay, yeah, I can give you some material, or even maybe give you a partial solution and then ask you to finalize that, or in an exercise, but it's yeah, I can show you how to do. I think it might be even in the, I have to check that if it's in the book. Usually I skip it, it's skipped because kind of the result is not so interesting. Yeah, okay. So if you don't have any, so we recall the 2D, 3D, and also some basics, or let's say even fundamentals. And then I will give you some related exercises, and then already reading at least, and then we continue with the 2D problems on Thursday. Okay, so let's stop